Hi there, this is Physics, Chapter 9, Thermal Properties of Matter, Lesson 2, Melting and Freezing. In this video, we will learn to relate how internal energy of a substance, meaning its internal kinetic energy and potential energy, how these are involved during melting and freezing process. In particular, we will answer these two questions. How internal energy of a substance changes during heating of a solid substance until it melts, and how internal energy of a substance changes during cooling of a liquid substance until it freezes. So let's start by recalling what we know about melting, but you may not fully understand yet. Melting occurs when energy is supplied to cause a solid to change into liquid without a change in temperature. During melting, thermal energy supplied to substance changes into internal potential energy of the substance in order to overcome forces of attraction. And thirdly, thermal energy supplied does not change to internal kinetic energy during melting. Hence, temperature remains constant during the melting process. Now, to help us understand how this internal energy changes, I will use this experiment as an example. This experiment is what physicists do to determine the melting point of ice. We will first set up the apparatus as shown with a simple retort stand holding on to a lab thermometer, and this lab thermometer are immersed into ice or crushed ice, which is initially at a temperature of minus 15 degrees Celsius. We will then start the heating of the ice by lighting up the Bunsen burner. We will then record the temperature at every single minute until all the ice melts and the temperature of the liquid water over here reaches 10 degrees Celsius. We will then plot a graph of temperature against time of this process. Now, the graph of temperature versus time of the ice until it melts into water at 10 degrees Celsius is shown in this particular diagram. From P to Q, the temperature of solid ice rises from minus 15 degrees Celsius to 0 degrees Celsius at Q. And from Q to R, the temperature remains steady at 0, even though heat is being absorbed as the ice melts. From R to S, the temperature of melted ice or water rises from 0 degrees Celsius to 10 degrees Celsius at S. So what happens to the internal energy of the substance as it gains thermal energy from the Bunsen burner? Now, recall from the kinetic model of matter what happens during a change of state in terms of the motion and forces between particles. From P to Q, the thermal energy from Bunsen burner causes the particles to vibrate faster. This thermal energy is converted into kinetic energy of particles, hence causing the temperature to rise from minus 15 to 0 degrees Celsius. Once ice reaches 0 degrees Celsius, which happens to be the melting point of ice, the thermal energy supplied by the Bunsen burner is used to overcome forces of attraction between the particles, hence causing the ice to melt. This thermal energy converts to potential energy and is stored in the substance. During Q to R, the speed of particles remain the same, since the thermal energy supplied by the burner are all converted to potential energy. Hence, temperature during this melting process remains the same. So during Q to R, the total internal kinetic energy does not increase. From R to S, once all the ice has melted completely, the thermal energy supplied from the burner now causes the particles in liquid state to start moving faster. Hence, thermal energy is converted to kinetic energy of particles, causing the temperature to rise from 0 degrees Celsius to 10 degrees Celsius at S. So, to summarize how the internal energy changes. From P to Q, the kinetic energy increases, so the temperature increases from minus 10 to 0. During this stage, the forces of attraction between the particles remains unchanged. However, the speed of these particles increases. From Q to R, melting occurs, so only the potential energy increases. Kinetic energy does not change, and so the temperature remains the same at 0 degrees Celsius. And from R to S, the kinetic energy increases, so temperature increases as well. So with that, I hope you can understand a little bit better how the internal energies, especially the kinetic, potential energy of the substance changes during a melting process. Now in the next few slides, we will start to discuss how this internal energy changes during the freezing process. Now to understand how this is involved, let us first recall some facts about freezing, or otherwise known as solidification process. Freezing occurs when energy is lost to the surrounding to cause a liquid to change into solid state without a change in temperature. This simply means that freezing, when it happens, the temperature remains constant. It doesn't change at all. During freezing, substance loses internal potential energy to the surrounding. This potential energy is transformed to thermal energy. The result of this is that the forces of attraction becomes stronger. And the last point is this: internal kinetic energy does not change during the freezing process. Hence, the temperature remains constant during freezing. So I will use this example to help us understand how internal energy is involved during this freezing process. This particular experiment is used to determine the freezing point of naphthalene. Naphthalene is usually used in this kind of experiment because it has a low melting point of about 79 degrees Celsius. Right? So what we do is simply this: we place a solid naphthalene into a boiling tube or a test tube, and we immerse this boiling tube into a beaker of water. We then turn on the Bunsen burner to heat up the water, and as a result, this will cause the naphthalene's temperature to increase until it reaches 79 degrees Celsius, at which it will start to melt. Once it has completely melted, and once its temperature has increased beyond 79 degrees Celsius, we will remove this whole setup and leave it on the side. And we will place a thermometer inside this liquid naphthalene to observe how its temperature changes or drops over time. And a plot of a graph of temperature against time will then be drawn out. Now, let's have a look at how the temperature of naphthalene changes when left to cool on its own. From A to B, the temperature of naphthalene falls from 90 degrees Celsius at A to 79 degrees Celsius at position B. 79 degrees Celsius is the freezing point of naphthalene. From B to C, the temperature remains steady or constant at 79 degrees Celsius, even though heat or thermal energy is still being released to the surrounding. Heat is still lost to the surrounding because, as this process is happening, it is occurring at 79 degrees Celsius, which is at a temperature that is higher than the surrounding room temperature. A surrounding room temperature is typically between 25 to 30 degrees Celsius. And do remember or recall that heat or thermal energy will be transferred from a hotter region to a cooler region. Alright, so from C to D, what happens is that the temperature of the naphthalene, which has totally solidified, will start to drop from 79 degrees Celsius to 60 degrees Celsius. So now let's have a look at how the internal energy changes during this process. From A to B, liquid naphthalene is hotter than the surrounding air. Hence, it loses thermal energy to the surrounding. This thermal energy comes from the kinetic energy of particles. And since the particles loses kinetic energy, this causes the speed of particles to drop. Correspondingly, the liquid naphthalene temperature will drop from 90 to 79 degrees, which is the freezing point of naphthalene. Now, during the freezing process from B to C, the particles will lose potential energy. This allows the formation of the strong bonds or the forces of attraction between these particles. As a result, the particles become closer together and they will start to solidify or freeze. Now, during this stage, the total internal potential energy of the particles decreases because it is lost as thermal energy to the surrounding. And during this process as well, the total kinetic energy does not decrease or does not change at all. As a result, the temperature remains constant during the solidification process. Take note as well, between B to C, naphthalene exists in a mixture of states. It is a mix of liquid and solid state. Now at point C, all the liquid naphthalene has changed into solid state. So from point C onwards, the naphthalene will still lose heat to the surrounding because it is still hotter than the surrounding air. So when this heat is lost to the surrounding, this heat, which is the thermal energy, comes from the kinetic energy of the particles. This causes the particles to slow down, and as a result, the temperature will decrease as well. So in summary, from A to B, the kinetic energy drops. Okay, from B to C, where freezing occurs, only the potential energy decreases, but kinetic energy remains unchanged. Hence, the temperature remains the same as well. From C to D, once all the freezing is complete, only the kinetic energy of naphthalene particles decreases, so the temperature drops as well. So to summarize melting point and freezing point, after looking at both cases, let's look at these 4 key ideas, alright, these 4 key points. Melting point is the temperature at which a substance changes from solid to liquid state. Freezing point is the temperature at which a substance changes from liquid to solid state. Take note that the melting point and freezing point takes place at the same temperature. And this temperature is different for different substances. So what we mean is, for example, ice or water, the melting point of ice and water and the freezing point in ice and water, they are the same at 0 degrees Celsius. For naphthalene, which is a different substance, the melting point and freezing point for naphthalene is at 79 degrees Celsius. So they are the same. But for different substances, this temperature, the melting point and freezing point, will be different. So going back to the lesson objective, which is to relate how internal energy of a substance, its internal Ke and Pe, how this is involved during melting and freezing process, we can summarize that during the heating or cooling process, as long as there is a change of temperature, the kinetic energy will change as well. As a result, the speed of particles changes and there is no change of state involved. However, when there is a state change from either solid to liquid, melting, or from liquid to solid, which is freezing, potential energy changes, but kinetic energy remains the same. So the temperature remains constant. Right, thank you.